turn that back on. So my first job is to define the port here. So let me do that. Add a new waveguide port. The face I want is this one. Select that. This I can leave the default. Properties. Give it a name, say WP1. Waveguide port definition, I want a 1 watt modal power feed. This picks up this component definition here. The 1 watt modal power feed is a predefined component. I'm going to define my impedance using the power voltage method. And as you know, voltage is path dependent. So I need to specify an impedance line that's going to be used to measure the voltage along. Just two endpoints. With microstrip, you want to go for the maximum voltage center to center, and that defines my impedance line for the impedance calculation. I'll do the same for port 2. We'll skip ahead and I'll add port 2. So adding port 2 is identical. I skipped ahead for you. But you'll notice that the ports still have a caution on them. It's saying the waveguide is not on the simulation bounding box. You have to have the ports on the outer surfaces of the simulation, because you can't simulate fields beyond the port, obviously. So I'm going to fix that by using my FEM padding. I'll just get rid of the free space. Now you'll see the caution symbols have gone away and the boundary of the simulation is right on the port planes. So now we're ready to simulate. I'm going to set up a simulation here. I'm going to use FEM. Now FEM is slightly different from the finite difference time domain we talked about before, the Yee cells. This uses tetrahedral meshing. It's an adaptive mesh, it's automatic, but it's kind of similar to, instead of using cubes, you're using tetrahedrons. So I'm going to use the iterative solver. The default is the direct solver. This machine's a 3-year-old laptop. It's only got 2 gigabytes of memory, and the iterative solver uses a lot less memory than the direct solver. And this particular structure doesn't have any convergence problems, so there's no disadvantage of using the iterative one. If you do get very complicated structures that don't converge with iterative, then you can use the direct solver, but you do need a pretty beefy machine, a desktop machine with decent amount of memory if you're using large structures. But iterative is fine for this case. And I've also altered the delta error, which is basically the change in the S parameters for each iteration. This is like 2% magnitude change in S parameters. This will be the criteria for the iteration to end. Once I get a smaller than 2% change in my S parameters, the iterations will stop, because I've converged to within that error on the Smith chart, a 2% error on the Smith chart. So I think I'm all set up here. I've got my frequency plan, start and stop frequency, how many steps I want, adaptive sweeping. I'm going to create and queue the simulation. Now this takes about 30 minutes to run, so after the first few seconds I'm going to fast forward and we'll look at the end results, because it's not very interesting watching a simulator run for 30 minutes. So I fast forwarded, my simulation's done now. It took about 30 minutes, 38 minutes in fact. This is a 3-year-old laptop, 2 gigahertz, 2 cores, 2 gigs of memory. Your mileage may vary, as they say. Let's look at the results. The results, I picked my project name. There's only one project right open now. I want the frequency results, the S parameter results. I can plot these on a linear graph. See the forward and return loss, the S parameters there. We can do a Smith chart also. Once you're satisfied with the results, of course you can export them to a city file format. I think I said touchstone before, I meant city. And you can import them into any tool, including the InfiniiSim software. Now the S parameters give you a good black box model of the structure, but sometimes you want to see inside the structure, so you'll hit on this advanced visualization button here. It'll load the appropriate project. So we can orbit around the structure in 3D. You can select a given plane and then check for connectivity. Kind of useful in case there's a little gap or something like that. Highlights. We'll do that again. Zoomed in, you can see how the bond wires light up and so on. You can also select a given plane, look at the gridding there, and animate the fields. Gotta choose a frequency. Let's choose the lowest frequency. Port 1, mode 1. Look at the E field, select the plane we want to visualize, and we need to enable that plane. See the fields pretty much in sync across the whole structure here. If I just zoom out here. If I go to the highest frequency, however, you can see how the mode pattern, field pattern breaks up. So here you get some insight into, let me just center this on the screen. I need to pan that one up there. You can see that the mode pattern, the field pattern, is showing this reflections and attenuated behavior. So that's the advanced visualization. Now let's go back to the slides.